Separable differential equations. The elementary differential equation is where you have dy dx and you just integrate it. It's just a function of x. No y's running around anywhere. So it's a function, a normal function, nothing parametric or anything going on. So what we do then is just to integrate it. Because every value of c, as we've discussed before, leads to a different solution, because you could have plus 2 plus pi minus e, whatever, and the derivative would be the same, then there are infinitely many solutions, but they're all the same up to a constant. So here we want to find the general solution for this, which is just basically integrate it. Oops. I'm doing wrong things. Hold on. Okay. So we just integrate. And over here, let me just point out one thing that might be useful to have thought about when we get later. So I can say now this, and then I integrate both sides, and over here I get y plus a constant. And because there's a constant on both sides, I can forget it. I can just pretend that both the constants are on the right side. Because if it's like y plus 3 equals this plus 5, then I would just subtract the 3, and I still have y equals this plus a constant, just a different constant. So that's what happens when you integrate both sides. And I think if you had just thought dy dx equals x squared minus 1, you automatically would have taken the antiderivative of that thing and then plus c. So this is just a slightly different way of writing what you already kind of felt in your heart of hearts was the thing to do. Okay. So dy So I've got 3 e to the minus 2x divided by minus 2 plus a constant, so minus 3 halves. And the dividing by minus 2 is because I would have multiplied by negative 2. When I took the derivative of this, it would have been e to the minus 2x times the derivative of minus 2x. Okay, but what if it's not like that? What if you have x's and y's running around on the other side also? So what I just did before was basically put y's on one side and x's on the other. The only thing is that before we had dy dx as a function of x, so the only place y made an appearance was in dy. But if you have y's on both sides, then you can't do that. You can't integrate that because you're not sure. You know how to find through implicit differentiation derivatives like that, but it's kind of unlikely that you can undo them with any tools you've learned in this course. But if you've got a function of x divided by a function of y, then you can just cross multiply and you once again have y's on one side, x is on one side, and now hopefully you can differentiate, anti-differentiate. Okay, so if I look at this one, I just put y dy equals x squared dx, so I've just cross multiplied, or if you want, multiplied through by y and then multiplied through by dx. Okay, so this is y squared over 2 equals x cubed over 3 plus a constant. So you can leave it like this. You can sort of like multiply through by 6 if you wanted. If I take 6 times every constant in the world, I still get back every constant in the world. So that's a little bit cleaner looking. You don't necessarily have to do that, but you should recognize what's happened, right? If you get this and it comes out like that, you should be able to kind of recognize what's going on. That's a messy box. Okay, so I'm going to put the y's together on one side, which means I've got to do dy. I didn't make a proper amount of space there. So this is, let me say first, remember that the situation we wanted was a function of y on the bottom and a function of x on the top. Well, there aren't any x's going on at all. Y's on the top, so we kind of have to do this so that it's function of y, function of x. But we could also just say that if dy dx is y minus 5, then if I divide by y minus 5 on both sides and divide by dx, so this first step gets me now I divide by, or I multiply by dx. Okay, so in either case, this is the same 1 over y minus 5 dy ends up this way. So one way or the other, you've got to get the y's on one side, x's on the other side, and the dy's and the dx's cannot be in the denominator. Because when we integrate, it's got to be blah dy or blah dx. So I'm going to integrate this. And this, hopefully, we don't get too discombobulated by this algebraic mess to forget the natural log. Everyone's favorite thing to forget. And there's a good chance this would not be left this way. Because that's kind of horrible, right? But I don't know why I clicked that. If I take e to both sides, I get y minus 5 equals e to the x times e to the c, sort of. So I have y equals some constant, e to the x plus 5. I don't know how it would look if you got this on a multiple choice for sure. There's a good chance that it'd still just look like this. Because really, you'd be, generally speaking, trying to solve for it when you know a y and an x, and then things would clean up a bit anyway, because this would become a number. So you should know how to at least move about between these things. When you're watching these, I hope you're pausing these and maybe trying some problems. Don't try to digest all of this in a sitting. I'm doing wrong things again. Okay, so okay, this is another one that's not fraction. It could be written that way. So we could say this is equal to e to the x over 1 over y squared. That's just to get it in the bottom. Or we could divide through by y squared, and then multiply through by dx. And then once I have it like this is y to the negative 2. Okay, so y to the minus 1 over minus 1 equals e to the x plus a constant. Whoa. I could now solve for y here. I could say so 1 over y equals negative e to the x plus a constant, because again, if I multiply all the constants in the world by negative 1, I still get all the constants. And then y equals 1 over this. This does not equal 1 over minus e to the x plus a constant. These are not equal, okay? All right, now an initial value problem, it doesn't necessarily mean the initial value. It gives you a value. And basically when you have a value, you can go back and solve for c. So that you don't have all the constants in the world. You have the one that makes, in this case, y of 0 equal to 5. And otherwise, it's the same. So this one's an elementary function differential equation. It's not separable. They're all x's. So I just say y equals x squared minus x cubed plus a constant. So that's just anti-differentiating this bit. And then I need to say, okay, when x is 0, y is 5. When it's a polynomial and they give you the actual initial value, like value at 0, it makes your life kind of easy because then that number is c. So y equals x squared minus x cubed plus 5. Okay, so this one, we've got a little more stuff to handle. Y minus 9 dy equals 3x plus 1 dx. Y squared over 2 minus 9y equals 3x squared over 2 plus x plus a constant. So y is 2 when x is 0. Sorry, I got distracted there for a second. So over here we have 2 minus 18. So minus 16 is c. So y squared over 2 minus 9y equals 3 halves x squared plus x minus 16. Okay, so now we have a constant times whatever the main function is. This is like probably area and time. That's what those usually mean, but at any rate, they're random. So we want to get dA over Ka, and don't cancel those a's, equals dt. So this is 1 over k times dA over A. Okay, so that could actually come out. So this is 1 over k times natural log A equals t. So we could say natural log, plus constant. Natural log A equals k t plus c, because this part, again, multiplied by k, you still get all the stuff back. So then e to this so I'm going to make a new, I'm going to do a capital K for this e to the c. This honestly still ranges over, this c was ranging over all numbers in the world. If you take e to all numbers in the world, you get all positive numbers in the world. So these are different k's. Let me maybe double bar that one. Okay? So if you have that the derivative is k times a, then a is a constant times e to a power. Of course, you've done derivatives of e to the something, and it's e to the something times the derivative of the something. So that's all this is saying, is that's the only way that the derivative is a scalar of the function, is when it's a power of e. Okay, so we have this. Just checking to see how much we have left. So we have this one. So we have an example that sales in thousand of a certain product are declining at a rate proportional to the amount of sales, with a decay constant of 15% per year. Okay, so I'm just going to grab this bit. And remember that for part B, we're supposed to find a general solution. So we've got to translate this first. So this says, sales in thousands of a certain product are declining at a rate, so ds dt equals proportional to the amount of sales, so some k times s, with a decay constant of 15%. So I'm just going to replace that k with a negative 0.15. Decay, so it's negative. So that means that s equals m, or double bar k, or whatever you want, times e to the minus 0.15 t. But we don't know what m is. So now instead of solving for a plus c, because it was on a power of e, it's a times instead. So we don't add plus c, we just put the m. The m's the thing we don't know this time. Okay, so sales is in thousands and time is in years. So now we want to suppose that when t is 0, sales are 2,000. Now we want to find out what is m. So when t is 0, sales are 2,000. Because s is already in thousands, I'm just going to put a 2. When I plug in 0, that's e to the 0. This is all just 1. So m is 2. So s equals 2 e to the minus 0.15 t. All right, so what will sales be after 6 years? S equals 2 e to the minus 0.15 times 6 to e to the minus 0.9. So I went over just to the computer very quickly and found that this is equal to 0.813. So S is 0.81314, but this is in thousands, so this is 813.14. And that is the end of this section.